Let us discuss the main ideas for the construction of the Lebesgue integral. So consider a function f defined on a set x. So think of x as the closed interval ab, for instance. So here we want to define a meaningful integral of f over x. So going back to the geometric interpretation of the integral of f would be the signed area of this shaded region on the leftmost drawing. So this would be the area of the upper part minus the area of the lower part. That would be the integral of f of x. So first, what we do is to write or decompose your function f into a difference of two non-negative functions. That would be f plus minus f minus. These are called the positive and negative parts of f, respectively. So what is the positive part of f? So that would be denoted by f superscript plus. So if the function is positive, then you take the function value. If the function is negative, then you take the value 0. So in other words, f plus would be the max between f and 0. So if you have a graph below the x-axis, you replace that by a 0 value. So in this case, this region will be replaced by the value 0. On the other hand, the negative part is obtained by, so first you take the negative of your function, and that would be the reflection with respect to the x-axis, and then you take the positive part of this. So that would be the max. So the negative part would be the max of negative f and 0. So in this case, since this is below the horizontal axis, we replace this by the 0 constant function. So this would be the negative part of your function f. It is obtained by reflecting and then taking the positive part of the reflection. So in this case, this integral would be the difference of the integral of the positive part and the negative part. Take note, the negative part of a function is also a non-negative function. The negative part of a function is also a non-negative function because here you take the max between negative f and 0. So it is always less than or equal to, it is always greater or equal to 0. So for this, take note that this is similar to what we have did with respect to the Riemann integral. So you consider it as a signed area where when you have the positive part, that's the area above the horizontal axis, minus the area below. In any case, both of these requires the definition of the integral or the Lebesgue integral for non-negative functions. Since both of these, the positive and negative part are non-negative functions. So here we need to define what is the integral of a non-negative function is. So for that, let us concentrate on the positive part at this point. The negative part can be done in an analogous manner. So first, what we do is we approximate f by a simple function. We will define what a simple function precisely later. And this a simple function is given as follows. So it's either alpha or beta. So if x is in some set, say A, and x in some set B. So in this case, this would be your set A, and this would be your set B. So if x is in A, then you have the value alpha. If x equals B, then you have the value beta. Of course, you can write A to be same as phi inverse alpha. So this is the inverse image of the singleton alpha containing alpha, and similarly B would be the inverse image of the singleton beta. So in this case, take note that your integral AB. So as I said, think of the moment x to be at the closed interval AB. The integral of your approximation is, let's say, can be computed straightforward. And this is alpha times the length of A plus beta times the length of B. And this will be the approximation of your integral corresponding to the positive part of your function f. So the question is, can we find or the goal is to find a sequence of non-negative simple functions such that the simple functions tends to or converges to your positive part. And we then define the integral of the positive part to be the limit of the integrals of your simple functions. And this will be somewhat the definition of the Lebesgue integral of a non-negative function. You can also do this for the negative part of f. Here, take note that we need to replace the length by a measure. And this requires the definition of integral for simple functions. So replacing here the length by a measure. So take note that A here is the inverse image of this singletons. Taking the measure of the inverse images requires the concept of measurable functions as we have discussed last time. So here, in order to take or in order for the inverse images to be measurable with respect to a given measure, the function phi must be measurable. So again, here is the or here are the main ideas for the construction of the Lebesgue integral. So first, decompose your function as a difference of two non-negative functions, namely the positive part and the negative part of f. And for this, one requires the definition of the integral for non-negative functions. Concentrating or taking into account the positive part, first you can approximate this by what we call a simple function. By this simple, we mean that the values is only finite. For this illustration, we have two values, namely alpha and beta. And the values are either alpha or beta, depending whether x is in A or x is in B in this figure. And we can approximate this integral of the positive part by the integral of this approximating simple function. As I said, this requires the definition of the integral for simple functions. So for the integral of the simple function, you can just take the, at least in this figure, you can take the sum of the areas of the approximating rectangles. So that's the height alpha times the length of the base. Here, the base are the regions or the sets A and B, which are inverse images. So here we need that it is measurable. The inverse images are measurable. I would like to emphasize here that the main difference, as we have discussed in the introduction of the Lebesgue integral and the Riemann integral, is that here we partition, or we at least approximate the range of your function, not on the domain. So here, the approximate values of the range is or two representative values of the range are denoted by alpha and beta. So with this discussion, we would like to define, provide definitions of the Lebesgue integral for, so the first step, we do this for simple functions. Next, we do this for non-negative measurable functions and for general functions. And we will be precise what functions are these later.